Welcome back. The next a couple of lectures and then what follows after that, a series of lectures that start with robust stability analysis, which is essentially looking at systems with uncertainty. And there are multiple ways of looking at it through frequency domain conditions, which is the classical approach, and even the more modern approach through MATLAB, we can say. But there are ways to connect these frequency domain conditions to time domain conditions, which is essential if we are dealing with nonlinear systems, especially a combination of linear and nonlinear systems. One has to understand how to solve these problems in the time domain, right? And then there is a more direct way of approaching these problems using Lyapunov functions, and we will look at eventually a lot of these things could be viewed as a special case of sector nonlinearities, and eventually the best approach is to understand this grand theory called dissipativity theory, which we will present in a few lectures, right? So, the first part, this is a three-part lecture, and the first part is frequency domain condition. And we will look at this model. We have seen a typical linear model as x dot equals ax, whereas we will add this component x dot equals ax plus b delta x. So let me motivate this particular model, right? So if we consider this typical say spring mass damper system, we can write the so-called system matrix or A matrix that we have been using in notation as 0, 1 minus k by m minus c by m, right? But if we somehow know that c is unknown exactly, so c is probably between, I don't know, minus some low value and minus minus some big value or something like that, it's between those two numbers, then we could rewrite this as some average value plus some uncertainty delta, right? So which makes this particular matrix A as A plus delta sub A, and this delta sub A can be written as B delta C, where delta is kind of isolated in the middle, right? So in general, basically I have something like A plus B delta C as my model, where I capture A, then the average part, so to speak, and B and C capture the structure of this matrix, and then D just focuses on the so essentially we can write the systems matrix as a nominal matrix A plus some uncertainty, where we have this A plus B delta C. B is the uncertainty, delta is B and C capture the structure, and delta is the uncertainty. So delta could be real scalar, it could be block diagonal, symmetric, or some other structure. So the trick of different results in robust stability analysis is essentially how best can we capture these different types of uncertainty, right? So anyway, going back to this model, x dot equals A plus B delta C times the x, then we can rewrite that as these three equations: x dot equals ax plus bu as if there is some input, and y is cx with some output, and u is basically the component that is connecting u and y through this uncertainty delta, and therefore this entire system could be viewed as a feedback interconnection between a nominal part whose transfer function is c times si minus a inverse b, and the uncertainty delta. Typically we will assume for the time being is delta is a constant, but it could actually be beneficial in some cases where this delta itself is a transfer function, though this particular example doesn't demonstrate that aspect, right? So what is the robust stability analysis problem? It's simply for a given set bold delta, some set of uncertainties, what are the conditions on G of S that will ensure feedback interconnection is stable for all the uncertainties within this particular set, right? And the result is relatively straightforward to state, right? The feedback interconnection of G of S and delta is stable for all uncertainties in that particular set, if and only if this determinant of I plus G of J omega times delta is not equal to 0 for all omega as well as uncertainty in the delta, right? So let's go back and try to understand where this is coming from. Some of you may recall Nyquist criterion. It's a fantastic application of complex analysis to stability issue, and which had very complex statement also, something like basically the number of encirclements and things like that. But when it comes to stability margins, which is essentially looking at an uncertain problem, we will see basically how we cross this point -1. In the scalar case, it becomes -1. In the what do you call the multiple multivariable case, basically, let's say this is my Nyquist plot for so say here we are dealing with delta G, a matrix, square matrix, and we will imagine that we basically draw eigenvalues of each of those things and pretty much draw the Nyquist plot. Let's say this is -1. So if I assume the nominal system G is stable, right, and this perturbation, what it will do is it will try to change the encirclements, because the number of encirclements, when it changes, we will go into unstable, from stable to unstable region, right? So essentially we are going to look at for all deltas which will cross this delta. So let's say this region is where determinant of I plus delta G is equal to 0. Okay, I mean, obviously it's not going to be that clean, but let's say something like that, right? So I'm going to basically try to find what's the biggest circle that can be given in this particular delta that will ensure this condition is not going to be satisfied. Inside that circle, the determinant is non-zero, right? And anyway, I mean, graphically it tries to give intuition, but it's really not best way of looking at it. There is an algebraic way of looking at it, and it's as simple as straightforward application of the basic Nyquist criterion to multivariable case, right? I say that in words. Basically, the proof depends on the generalized Nyquist criterion. But let us pause for a second and understand what this means. So we are asking that to check determinant of G of S and delta, take those two matrices, determinant of I plus G times delta for all values of omega and also for all values of delta. Okay, so how many elements are there in this delta? Probably infinite, and then omega infinite. So this can never be a computational method to check. So it's impossible, just like our basic epsilon delta definition of stability, right? So therefore this is not a good criterion. So people have been looking therefore for ways to get around that. So for example, the so-called structured single value, or mu, is essentially trying to capture this information in a measure theoretic purpose, and then gives a measure of allowable uncertainties and things like that. But in some sense they take this definition and give their definition, and they are one and the same. It's slightly small, provide some kind of sizing the level of uncertainty, but essentially it also boils down to checking that determinant conditions throughout, right? So therefore they provide ways to compute it, but even they have its own difficulties. And then one such condition is this so-called small gain theorem, right? And what is a small gain theorem? So we'll consider the set of uncertainties given in this particular case as all those uncertainties whose maximum single value of delta is less than or equal to 1, right? I hope enough linear algebra to realize that basically maximum singular value of any matrix is a nice way to capture. It's a induced norm, and one of the best ways to capture the size of this thing, right? So then the small gain theorem essentially says that the feedback interconnection of G of S and delta, which is going back to the stability of the uncertain system, is stable for all delta belonging to delta if and only if sigma max of the maximum singular value of G of omega, J of J omega, is less than 1 for all omega, right? And this necessary and sufficient conditions is kind of a tricky thing. You have to really analyze, understand under what conditions and things like that. But at least as a sufficient condition, if the maximum singular value of G of J omega is less than 1 for all omega, then we are guaranteed to have this stability of the feedback interconnection, right? So from the determinant condition we came here and we eliminated at least checking for every uncertainty. We are not far off, we still have to look at this maximum singular value condition for every omega, right? But unfortunately this particular thing is such a way that we just take some set where all we look at is the size, right? But many a time we'll have structure within that set, right? So therefore this is not a good condition for uncertainties which has some nice structure, right? What kind of structure is possible? One possible structure is block diagonal, and perhaps when we look at a couple of examples we'll see how those block diagonals come and things like that. But for the timing, let's assume that this delta could have actually a block diagonal structure, which means it's mostly 0 except the blocks in the middle, right? So if we implement this sigma max of g less than 1, it's allowing all possible uncertainties that are not even block diagonal. So that means typically you may not get a good condition for stability. So we can actually do better if we somehow respect this particular structure, right? So therefore there is an extension to this particular result, and essentially that requires this set of scaling matrices D, which basically you have this block diagonal structure. So you can imagine a set of scaling matrices where each and every one of these scaling matrices will commute with the uncertainty, right? Suppose the uncertainty has 2 blocks, then the D also will have correspondingly 2 blocks. If each of those blocks is full block, then the delta the D part, the scaling part, will be scalar and vice versa. So let me state the result and then show you perhaps different possibilities of scaling matrices. So the feedback interconnection of G and delta is stable for all delta in this block diagonal set if and only if there exists a scaling matrix such that sigma max of D times G times D inverse is less than 1. Now this is a nice extension of this particular structure of the delta, but because of this D, perhaps when D is identity, this condition may not be satisfied, but by putting the structure, perhaps it's satisfied, right? That is the hope, right? Still very much possible that D becomes identity, and then this is actually going to be allowing all kinds of uncertainty. So let me show you. Suppose the delta matrix has some delta 1. The first one is full matrix, and let's say something like this, right? Here there is no additional structure and things like that. So then the scaling matrix could be chosen something like D1 times I 0 0 and some D2, okay? So you can clearly see D delta is going to be equal to delta D, and can we find such D, okay? D1 is 0, D1 identity is 0, D2 times G D inverse sigma max of that is less than 1, okay? So one of the nice things about this particular matrix is it's almost equivalent to looking at condition G star actually D square minus D is less than 0, square is less than 0, but you can imagine doing the same thing from some other D hat or something like that. And so now the test for the small gain condition essentially translates to checking for possibility of D hat, which is a matrix with this particular structure, and solve this particular LMI. So this is a LMI feasibility problem, okay, for some structured variables. So this D is a structured variable. Can we find that structured variable such that this is satisfied, okay? And this is one way of looking at it. There are possibly other ways of doing things, but this particular condition, like the small gain theorem, suffers from the same drawback, that this particular condition, that LMI has to be checked for every omega, okay? So more general theorem, which is actually some favorite, which will eventually connect things to our what do you call dissipative theory, is go something like this. If you have some matrix QRS and then your set is dependent on this delta, sorry, in these three matrices QRS, such that this set is true. Okay, then we can state a condition if G of S is such that this frequency domain condition is satisfied, then we can show that the feedback interconnection of G and delta is stable, right? So you can imagine basically if I pick S to be 0 and then Q to be minus identity, R to be identity, that becomes the small gain version. And if you pick Q and R to be, say, Dn minus D, then you'll get the standard small gain theorem. And then there are other conditions. In fact, let me show you a little bit. Suppose if we have something like delta equals delta times identity, single block, and there's no otherwise block. Even in this particular case, we can pick D to be a set of all these things, basically full blocks, right? N by n, and you can clearly see D delta is equal to delta D. So at least this has a very specific structure of diagonal delta, so that can be enforced through the small gain theorem where D and delta is commute. But actually we also can do some magical trick like this. Basically, the fact that this delta is real, let's say, ensures that if I actually multiply something like, let me say some n matrix, it's a full matrix, then it's Q Hermitian. Then let's see what happens. If I take n times delta and then take Hermitian part of that, then I'm going to get this kind of a thing. And since delta is real, this part is delta, and then n star is minus n, right? So essentially this also becomes Q sorry, if I pick something like Hermitian, then we can ensure that everything remains Hermitian, and you'll get n delta is equal to delta n, and using this generalized equality, we can actually show that by picking a particular S is equal to some your imaginary number times n, that guarantees not only the structure block diagonals, in this particular case diagonal structure, but also guarantees some kind of the real part of the delta, right? And then we will look at an example carefully in a couple of lectures later, right? So this is the most general result, and then the proof is quite interesting. Basically, let's say we are trying to avoid determinant of I plus G delta is equal to 0. So let's assume to the contrary that it is 0 for some omega. Then basically you have to have a non-zero x such that this true, x is equal to minus G delta x. That's what the definition of determinant is. But we know that this delta part is less than or equal to 0. So 0 is greater than or equal to this x star times this entire expression times x. And by expanding it and then actually using the fact that x equals minus G delta x, we will you can manipulate it in such a way that the final expression looks like x star delta star times the one in the middle involves the expression of this G star condition, right? G star QG condition. But then we know that that's positive, so therefore this entire thing, since x is non-zero, is going to be positive, right? So how do I know delta x is non-zero? Because x is minus G delta x, so you better have non-zero. So all these things will point out that this is greater than 0, which is showing that 0 is greater than or equal to 0, which is a contradiction. So therefore there is no delta for which this determinant condition is satisfied. So it's a very cool result, in my opinion. Basically have this very general expression for the set of deltas, and then basically one single simple condition, and this specializes to pretty much every result that is there in robust control that is computable. Okay, and this has been enough literature that talks about how to use this kind of result to show different upper bounds for structured single value and things like that. All that is captured in your MATLAB robust control toolbox. Okay, so yeah, as I repeat myself, this specializes to every result connected to linear robust stability analysis. This has the drawback of every other result that we've been talking about, is basically all these frequency domain conditions need to be checked at every frequency, right? Computationally, it's a very expensive thing to do. Second thing is basically there's no way that we can guarantee that we are not missing some specific key points where that condition could be violated, right? I mean, some continuity conditions and things like that may help, but not beyond that, right? Whenever we use Nyquist plots or Bode plots and things like that, it's a semi-analytical. We have the picture in front, but we actually have a analytical way of convincing that that picture makes sense, right? But when it comes to MIMO systems that we are dealing here, if it is simply some matrix condition that is in frequency domain, then checking that is going to be very difficult.